In section 2.6, we'll be going over derivatives and rates of change. Now, the problem of finding the tangent line to a curve and the problem of finding the velocity of an object both involve finding the same type of limit, as we'd seen in section 2.1. This special type of limit is called a derivative, and we will see that it can be interpreted as a rate of change in any of the sciences or engineering. Now, we're going to be talking about tangents here. So if we have a curve C that has an equation y equals f of x, and we want to find the tangent line to C at the point P, A, and then f of A, then we consider a nearby point Q x f of x where x does not equal A, and then compute the slope of the secant line PQ. So again, we're picking a point on the line here. So here is your first point. And then we picked an additional point here. And what we're doing is we're trying to find the slope of that particular line, which is the secant line. So we're taking a change in y over the change in x. So we have f of x minus f of a over x minus a. Now, if we move a little further with this, okay, we can see that when we let Q approach P along the curve C by letting x approach A, then the slope of that line PQ approaches a number m. And then we defined the tangent T to be the line through P with slope m. This amounts to saying that the tangent line is limiting position of the secant line PQ as Q approaches P. So if we take a look at this figure here, okay, so here let's say you have your 2 points here, it's a secant line. And then we're getting closer by choosing another point here. Then we choose another point over here to ultimately get the line that's in red that's tangent to that curve at that particular point. Now the definition states that the tangent line to the curve y equals f of x at the point PA f of a is the line through P with the slope of the following. So m is going to equal the limit as x approaches a, f of x minus f of a over x minus a, provided that this limit exists. Okay, so the first thing we want to do is we want to go ahead and go through example number 1. And what we want to do is we want to be able to find an equation of a tangent. And we're going to find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. Okay, so the first thing we need to take a look at here is that we have a point here, and we're going to consider that first point from the given information that a is going to equal 1. Okay, and then our function states that it's going to equal x squared. Okay, so what we want to do is we're going to use that formula that's given to find that slope. So the formula that we're using is m, which is equal to the limit as x approaches a of f of x minus f of a over x minus a. And so what we've determined is that a is equal to 1. So now we're going to say now that the slope m is going to equal the limit as x approaches 1, okay, of the function f of x minus f of 1 all over x minus 1. And now what we're going to do is we're going to substitute the given information. So we have m, which is equal to the limit as x approaches 1. And from the given information, we can see that f of x is equal to x squared. So we're going to replace f of x to be x squared. Okay, and when the input is 1 at that point, then the output over here is 1. So it's going to be x squared minus 1 all over x minus 1. Okay, so now what we're going to do is we're going to go ahead and then evaluate this limit. But before we do that, we need to factor so we can simplify this a little further. So we can factor this by the difference of squares. What's happened is we can simplify that. And so now we have the slope, which is equal to the limit as x approaches 1 of x plus 1. Okay, so now we can go a little further by plugging in the value of 1 as we evaluate this limit. And for x, so we got 1 plus 1, and therefore the slope is going to equal 2. Now in step number 2, what we want to do now is we're trying to find an equation of the tangent line to that parabola. So now we're going to have to use our point slope form to find that equation. Okay, so we know that the point is 1, 1, and we know that our slope is 2. So now we're going to have y minus 1, which is equal to 2 times x minus 1. And we get y minus 1, which is equal to 2x minus 2. And then ultimately the line is going to equal y, which is equal to 2x minus 1. All right, next. Now, we sometimes refer to the slope of the tangent line to a curve at the point as the slope of the curve at the point. And the idea is that if we zoom in far enough toward the point, the curve almost looks like a straight line. And if you look at these three figures here, okay, it's going to illustrate this procedure for the curve y equals x squared, which is what we did in example 1. So the more that we zoom in, the more the parabola looks like a line. So in other words, the curve becomes almost indistinguishable from its tangent line. So if you look here, as you zoom in further and further to the right, it becomes a possible straight line there. Now, let's go ahead and take a look at an animation of this situation. Okay, so here we have the curve f of x, which is equal to x squared. All right, so here's our parabola. Okay, and then what we can do here is that if we want to, visually see it closer, to see where it says magnification down here, it just kind of increases the zoom much more clear for you to see what's happening over here. Okay, now over here, I want you to notice what's happening here. We're going to see the value of a, right? So when a is -2, the slope is at 4. Okay, and as I keep getting closer and closer to 0, okay, you see what's going on with this line, okay? Keeps going, it keeps going, it keeps going, it keeps going, it keeps going. And then all of a sudden, when it gets to 0, it's a horizontal line, okay? And therefore, we can see that the slope is 0. Now, that's going to be important as we look forward into our discussion. And then if we keep going to the right, you can see what's happening with this line, okay? So that's a good sort of animation of kind of what we've seen in our first example. All right, now there is another expression for the slope of the tangent line that is sometimes easier to use. So if we know that h is equal to x minus a, and if we solve for x, then x is going to equal a plus h. And so the slope of the secant line of PQ is the following, where you have f of a plus h minus f of h. Okay? Now, we'll look at that figure where we have the case of h is greater than 0, okay, and q is to the right of p, and if it happened that h was less than 0, q would be to the left of p, okay? Now notice that as x approaches a, h approaches 0 because h is equal to x minus a. And so the expression for the slope of the tangent line in a definition becomes the following, which is m, which is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Okay, now you can see what's happening with this graph. Okay, now what we've done is we've added h to the value of x. Okay, and then you can see what's happening according to this graph. All right, so let's take a look at example number 2. Okay, for example number 2, what we want to do is we want to be able to find an equation of the tangent line to the hyperbola y equals 3 over x at the point 3, 1. Okay, so if you take a look at this given information, we know that the function is given. So f of x is equal to 3 over x. Okay, and then we can also determine that the point 3, 1 okay, it's stating that the slope is tangent at the point 3, 1. And so therefore that tells us that a is equal to 3. Okay, now using that formula, okay, we have the limit. So in step 1, m is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Okay, so now that we know that a is equal to 3, now this becomes the limit as h approaches 0, and now this becomes f, replacing a with 3, so this is going to become 3 plus h minus f of 3 over h. So now over to the side here, I'm just going to write down what happens when you get f of a plus h. Well, that becomes the input of the function. So now that becomes 3 over a plus h. Okay. And then what does f of 3 equal? Well, f of 3, if we plug that into the function 3 over x, that becomes 3 over 3, which is equal to 1. So now we can replace those into our current limit. So now we have the limit as h approaches 0, f of 3 plus h. Okay, and I'm going to put this as 3. This should have been a 3 there. So we have 3 over 3 plus h minus 1 all over h. So there's many ways to be able to go about this problem. You know, we can first multiply everything by h, or we can combine the numerator by using our denominator. So we know that 1 is the same thing as the fraction 3 plus h over 3 plus h. And again, this just becomes down to your algebra. Okay, and so now if we go a little further here, we're going to have the limit as h approaches 0 of 3 minus 3 plus h all over 3 plus h. We're dividing that by h. Okay, now if we combine like terms, you can see that when you distribute this minus sign, what we end up with is the limit as h approaches 0. 3 minus 3 is 0, and then distributing that sign is negative h over 3 plus h divided by h. Okay, now what we can do now is we can multiply the numerator and denominator by 1 over h. And by doing so, we're going to end up with the following. We have the limit as h approaches 0. We can simplify the h's, and so what's left is negative 1 over 3 plus h. And then those h's also are simplified. So now what we're going to do is now we're going to be able to evaluate it when h approaches 0. So we're going to get m, which is equal to negative 1 over 3 plus 0, which is equal to negative 1/3. So now we have our slope. So what we have is our slope and our point that it's passing through. So the slope is negative 1/3, and the point is at 3, 1 from the given information. It's not using the slope point slope form. Y minus y1 equals m times x minus x1. So we have y minus 1, which is equal to negative 1/3 times x minus 3. So now if we distribute the 1/3, we get negative 1/3 x plus 1. Add 1 to both sides, and y is going to equal negative 1/3 x plus 2. Now, if you take a look at the graph here, okay, this equation is written in a different form, which means that what they're doing here is they're multiplying everything by 3 to then make it a more clean look. So if we multiply everything by 3, we're going to have 3y equals negative x plus 6. So if we set this entire thing equal to 0, we would get x plus 3y minus 6, which is equal to 0. Okay, now in section 2.1, we investigated the motion of a ball dropped from the CN tower and defined its velocity to be the limiting value of average velocities over shorter and shorter time periods. So in general, suppose an object moves along a straight line according to an equation of motion, which is s, which is equal to a function of time, where s is the displacement, meaning the direct distance of the object from the origin, at time t. Now the function f that describes the motion is called the position function of the object. So in the time interval from t is equal to a to t is equal to a plus h, the change in position is f of a plus h minus f of a. So therefore, the average velocity over this time interval is the following. So the following average velocity is equal to the displacement over time, which is equal to f of a plus h minus f of a over h. Now, this is going to be the same definition as the slope of the secant line that we discussed for PQ in this figure here. Okay, so now suppose we want to compute the average velocities over shorter and shorter time intervals between a and a plus h down here. In other words, we're going to let h approach 0. So as in the example of the following ball, we define the velocity or the instantaneous velocity v of a at time is equal to a to be the limit of these average velocities. So therefore, this theorem here for number 3 states that the limit as h approaches 0 of f of a plus h minus f of a over h is the average velocity. So this means that the velocity at time t equal to a is equal to the slope of the tangent line at p. So now let's use this information to then solve our next example. Our next example is the following question. The velocity of a falling ball. Suppose that a ball is dropped from the upper observation deck of the CN Tower 450 meters above ground. And what we want to know is, what is the velocity of the ball after 5 seconds for the first part of this question? Okay, so when it's asking us what is the velocity of the ball after 5 seconds, we determine here that t is going to equal 5. And then we also need to know the equation of the motion. Well, what is the equation of the motion? Well, the equation of the motion is s, which is equal to the function of time, and that function of time is going to equal 4.9 t squared. So those two things are given. Okay, so now what we want to do is we're going to take a look at the average velocity. So the average velocity v of a is going to equal the limit as h approaches 0 of f of a plus h minus f of a over h. And so now what we're going to do is we are now going to take this function, and now this is going to become the limit as h approaches 0 of the number 4.9 times a plus h squared, since that is the input for the equation of the motion. So that's going to be 4.9 times a plus h squared minus 4.9 times a squared over the value of h. So now let's expand this a little further. So if we expand this a little further, we would end up with 4.9 times a squared plus 2ah plus h squared minus 4.9 a squared all over the value of h. Now, if we notice in the numerator, there are two terms that have 4.9 as a common factor. So if we factor out 4.9 from those two terms, then what's left is going to be a squared plus 2ah plus h squared minus a squared over h. Okay, so what that allows us to do now is to simplify the a squared and minus a squared. So now what's left is the limit as h approaches 0 of 4.9 times 2ah plus h squared over h. And again, continuing to use our algebra, we're now going to factor out the h. So we have 4.9h times 2a plus h over h. And then what happens there is we can simplify the h. And so now what we're left with is the limit as h approaches 0 of 4.9 times 2a plus h. So now if we evaluate this limit according to when h is 0, we now end up with 4.9 times 2a plus 0, and that's going to represent our average velocity. Okay, and if we multiply that out, then we should end up with 9.8a. So to complete this, we want to be able to find the velocity after 5 seconds. So what is the velocity after 5 seconds? Well, now what we're going to do is we're going to plug that into our function here. So the velocity after 5 seconds when a is 5 is then 9.8 times 5, which is equal to 49 meters per second. Okay, so that gives us the velocity after 5 seconds. Now, we want to know how fast is the ball traveling when it hits the ground. So we know that the deck is 450 meters above ground. Okay, and the ball will hit the ground at time t. So that means that the ball will hit the ground at time t. And we're going to call that t subscript 1, okay? And that is when s of that time t1 is going to equal 450. And now recall that s of t from our first step is equal to 4.9 t squared. So now we can say that 4.9 t subscript 1 squared is going to equal 450. Now, if we divide both sides by 4.9, then we know that t1 squared is going to equal 450 divided by 4.9. And so taking the square root of both sides, we're always going to take the positive value of time. So it's going to be the square root of 450 over 4.9. And that's going to be approximately 9.6 seconds. Therefore, the velocity of the ball as it hits the ground is going to be the following. So we're going to take the velocity at t1, okay, and that was 9.8 times t1, which is equal to 9.8 times 9.6, which is approximately 94 meters per second. Okay, now we're going to talk about derivatives. Now, we have seen that the same type of limit arises in finding the slope of a tangent line or the velocity of an object. So in fact, the limits of the form of f of a plus h minus f of a over h as the limit as h approaches 0 arise whenever we calculate a rate of change in any of the sciences or engineering, such as the rate of reaction in chemistry or a marginal cost in economics. Since this type of limit occurs so widely, it is given a special name and notation. So for number 4, here's a definition. So the derivative of a function f at a number a is denoted by the following. Okay, now the way that it is read, it is read as f prime of a. So the derivative is now considered f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h, if this limit exists. Now, if we write x is equal to a plus h, and then we have h, which is equal to x minus a, and h approaches 0 if and only if x approaches a. Therefore, an equivalent way of stating the definition of derivative is what we have in Theorem 5. So f prime of a would equal the limit as x approaches a f of x minus f of a over x minus a. Okay, now for example number 4, okay, we want to be able to calculate at a general number a. We want to find the derivative of the function f of x, which is equal to x squared minus 8x plus 9 at the number a. So the way to approach this is the following. Okay, so we have our definition, and our definition states that f prime of a is the derivative, which is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Okay, so now this is going to equal the following. You're going to have the limit as h approaches 0. And now we're going to substitute a plus h into this function. So that means we're going to have, instead of x, it's going to be a plus h squared minus 8 times a plus h plus 9 minus, we're going to substitute a now into that function. So it's going to be a squared minus 8a plus 9. And we're dividing this by h. Okay, now let's expand this a little further by using our multiplication. So in our numerator, we're going to have a squared plus 2ah plus h squared. We're going to distribute the minus 8, so minus 8a minus 8h plus 9. And then we're going to distribute this negative sign to get minus a squared plus 8a minus 9 all over h. And then what can we simplify here? Well, we can simplify the a squareds. We can simplify the minus 8a and plus 8a. And then we can also simplify the plus 9 and the minus 9. So now we end up with the limit as h approaches 0 of 2ah plus h squared minus 8h over h. And then can we simplify the h by factoring out something from the numerator? Well, we can factor out the h. And what's left is 2a plus h minus 8 divided by h. So now we can simplify the h. So now this becomes the limit as h approaches 0 of 2a plus h minus 8. And now we can apply the limit as h approaches 0. So we're going to have 2a plus 0 minus 8, which ultimately gives us 2a minus 8. Okay, so we defined the tangent line to the curve y equals f of x at the point P, A, f of a to be the line that passes through P, and has a slope m given by equation 1 or 2. So therefore, by definition 4, this is the same as a derivative, and then we can now say the following. Okay, we can say that the tangent line to y equals f of x at a point a f of a is the line through a f of a whose slope is equal to the derivative of f at a. And then if we want to use the point slope form of the equation of a line, we can write an equation of the tangent line to the curve for the following. So this might be something that's really important you want to make note of. This is the point slope form. So you would have y minus the function at a is equal to the derivative of a times x minus a. Okay, now let's take a look at example number 5. We want to be able to find an equation of the tangent line to the parabola y is equal to x squared minus 8x plus 9 at the point 3, negative 6. Okay, so if it's at the point 3, negative 6, this tells us that a is equal to 3 and that the output f of a would then equal negative 6. So we're going to use that function f of x which is equal to x squared minus 8x plus 9. Okay, and so we also determined from the previous example that f prime of a, meaning the derivative, was the result of 2a minus 8. And then recall that that is the actual slope. Okay, and so again, as we stated before, using the point 3, negative 6, we again determined that a is equal to 3. So what happens at the derivative f prime of a? Well, what does that mean? That means you're going to substitute 3 in for a. So this is going to be 2 times 3 minus 8. And that gives you the value of negative 2. So now let's use that point slope form from the previous slide. And that point slope form was y minus f of a, which is equal to f prime of a times x minus a. So we have y minus, well, f of a from the beginning of the problem is equal to negative 6. So we know that that's equal to negative 6. We know that f prime of a, which is the slope, we just determined that that was negative 2. And then this is going to be x minus the value of a, which is 3. So now let's go ahead and then solve. So we have y plus 6, which is equal to negative 2x plus 6. And then solving for y is going to equal negative 2x. Now let's take a look at that graph. Okay, so you can see the parabola here that it forms. There's the point on a line 3, negative 6. And what we've been able to determine is this line that is tangent that passes through that point 3, negative 6. And therefore, that line that we got was y is equal to negative 2x. Okay, now, next thing we want to talk about is rates of change. Now, suppose y is a quantity that depends on another quantity x. Thus, y is a function of x, and we write y is equal to f of x. So if x changes from x1 to x2, then the change in x, also called the increment of x, is the following. So when they write the change of x, you write this triangle. So the change of x would mean that you're finding the value of x2, which is the second x, minus the first x. Okay? And then the corresponding change in y would be the following. So if we want to write the corresponding change, and we use that triangle as the change in y, well, that would be f at x of 2 minus f at x of 1. Okay? And then if we want to be able to find the difference quotient, that means you would write the change in y over the change in x, which would equal the following. It would be f of x2 minus f of x1 divided by x2 minus x1. And so what you can see now is that this is called the average rate of change of y with respect to x over the interval from x1 to x2, and can be interpreted as a slope of the secant line. And in this figure, you can see that that is the slope of the secant line. Now, by analogy with velocity, we consider the average rate of change over smaller and smaller intervals by letting x2 approach x1, and therefore letting change of x approach 0. Now, the limit of these average rates of change is called the instantaneous rate of change of y with respect to x at x is equal to x1, which is interpreted as the slope of the tangent of the curve y equals f of x at p at x1 and f of x1. So for number 6 in theorem 6, the instantaneous rate of change is equal to the limit as the change of x approaches 0 over the change of y over the change in x is equal to the limit as x2 approaches x1 of the f of x2 minus f of x1 over x2 minus x1. Okay, so we recognize this limit as being the derivative, and we know that one interpretation of the derivative is as the slope of the tangent line to the curve y equals f of x when x is equal to a. So now we're going to have this second interpretation. We can say that the derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to x when x is equal to a. So now let's take a look at this graph. Now the connection with the first interpretation is that if we sketch the curve y is equal to f of x, then the instantaneous rate of change is the slope of the tangent to this curve at the point where x equals a. So this means that when the derivative is large, and therefore the curve is steep, as at the point P here in this figure, the y values change rapidly. So when the derivative is small, then you can see that the curve over here is relatively flat as at the point Q, and the y values change slowly. So again, at the value of P, okay, the curve is steep. Okay, and because it is steep, right, the y values change rapidly. Okay, and then at point Q, okay, the curve is relatively flat. And so therefore the y values change slowly. Now, in particular, when we talked about the position function where s is equal to f of t of a particle that moves along a straight line, then f prime of a is the rate of change of the displacement s with respect to the time t. So in other words, f prime of a is the velocity of the particle at time t is equal to a. So the speed of the particle is the absolute value of the velocity, and that is the absolute value of the derivative. So in the next example, we're going to discuss the meaning of the derivative of a function that is defined verbally. Okay, so the first question says derivative of the cost function. So a manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of this fabric is C is equal to F of X dollars. Okay, it says, what is the meaning of the derivative F prime of X and what are its units? Well, for part A, we can say that the derivative F prime of X is the instantaneous rate of change C with respect to X. So the way we would write this as F prime of X is equal to the limit as the change of X approaches 0 of the change of C over the change in X. So it says now in practical terms, what does it mean to say that f prime of 1000 is equal to 9? Before we answer that question, let's talk about those units. Okay? Since we know that the change in C is measured in dollars, and the change in X is in yards, then the units for f prime of X would be dollars per yards. Now again, going back to question B, it says in practical terms, what does it mean to say that f prime of 1000 is equal to 9? Well, what it's saying here is that after 1000 yards of fabric, the rate at which production cost is increasing is $9 per yard. Okay, now for part C, okay, it's asking us which do you think is greater, f prime of 50 or f prime of 500? And then what about f prime of 5,000? Now, the rate at which the production cost is increasing per yard is probably lower when x is 500 than when x is 50, because the cost of making the 500th yard is less than the cost of the 50th yard because of the economics of scale. So we could say that f prime at 50 is greater than f prime of 500. Okay, and then what can we say about f prime of 5,000? Well, as production expands, the resulting large-scale operation might become inefficient, and there might be overtime costs. Thus, it is possible that the rate of increased costs will eventually start to rise. So it may happen that f prime of 5,000 could be greater than f prime of 500. Okay, in example number 7, we want to find the derivative of a tabular function. Okay, so we're going to let d of t be the U.S. national debt at time t. So if you look at the table on the left, okay, this gives the approximate values of this function by providing end-of-year estimates in billions of dollars from 1980 to 2005. And what we want to do is we want to interpret the estimate and estimate the value of d prime of 1990. So the derivative d prime of 1990 is going to mean that the rate of change of d with respect to t when t is equal to 1990, that is the rate of increase of the national debt in 1990. Okay, so let's take a look at that. So we're saying here that the d prime of 1990 is going to equal the following. It's going to equal the limit as t approaches 1990 of the following function: d of t minus d of 1990 divided by t minus 1990. Okay, so I have this table on the right here, and these are all the values that we're going to end up getting according to our formula. But let's go ahead and do a few of them here. Okay, so let's take a look at these two values here. Let's say that we want to look at 930.2 and 3,233.3. So if we want to find the average rate of change, so we're going to take y, which is 930.2, and subtract our other y value, 3,233.3, and then divide that by our x2 minus x1, which is 1990. So we're using those values there for t. Okay, and that's going to give us a number of 230.1, and you can see that's where that value is. Okay. Now, we can continue to do that in order to find these values at 1985, 1995, 2000, and 2005. So that's going to give us the rest of these values. But what we want to do is we want to be able to find the average, okay, of these two slopes, because 1990 is in between these two numbers, correct? So 1990 is in between 1985 and 1995. So this means that here, this is going to give us d prime of 1990. And so what we want to do is now find the average. Now by finding the average of that, is by taking the average of those two numbers, which is 257.48 and adding 348.14 and then dividing that by 2, which then gives us the result of 302.81. So now we can say that d prime of 1990 is going to be approximately $303 billion per year.